Well, good afternoon. Some people still trying to find their place. We have still some empty chairs in the first row. My name is Michael Hausenblas. I'm Chief Data Engineer at MapR, responsible for EMEA. And in my daily job, I essentially work a lot with our customers, looking at the data sets and based on the business requirements, then coming up with architectures. Today I'm going to talk about predictive analytics, using Hadoop and the Hadoop ecosystem. I think it's fair to say that recommendations nowadays are really everywhere. No matter if you look at media, advertising, e-commerce, Amazon or whatever. And more and more we see that also within the enterprise boundaries. One example would be Cisco, one of our partners and customers, where they use recommendation systems essentially to recommend sales opportunities to partners. And they made some 40 million revenue increase in the first year, processing some 1.5 billion records per day using our platform. But there are also other machine learning applications like classifications. And again, just some short examples from our customer base. Return path, essentially doing IP address blacklisting based on that. Science Bank using that in the fraud detection area, essentially identifying anomalous patterns in the transactions and to see what is fraudulent and what is not. And one of the Fortune 100 telcos that has deployed a kind of customer 360 application, so being able to categorize the customers and score them. And all of them essentially use our platform, and on top of that, various ecosystem components, and one of the configurations I'm going to talk about later in greater detail. But before we come to that, some basics around that. So, although some physicists might disagree, I still say physics is kind of simple if you compare that with human behavior. So trying to understand why a certain person has clicked on a certain link, or determining what is fraudulent behavior and why is that so, this is really very complex endeavor. And one of the insights published by this rather well-known group of people from Google, the unreasonable effectiveness of data, is that if you have a lot of data available, and it's easy to say that if you're Google, admittedly, then it's not necessary to come up with very complex models. So a lot of data plus simple models outperform complex models. And it turns out that under this paradigm, essentially the algorithms are less and less important. So very naive, simple algorithms actually, again, with the respective amount of data, perform quite well. So most of these algorithms, when it comes down to, is really very simple math. I'm going to show you one example later on. Essentially metrics manipulation. It's really not much more than counting and some other simple math. And getting more data, as you can imagine, can really improve your results, factor 2x or whatever, while tweaking the machine learning algorithms might only yield a tiny percentage approval there. And obviously, you have to deal with and think about what I call data genitoring or data wrangling. Being able to acquire the right training data and the right amount of the data, massaging the data, getting the right features out there, and being able to do that at scale can pose quite some challenges. So one of the problems, if we're talking about large-scale data processing, machine learning in that area, is that you can't really rely on a domain expert to label, to annotate the data. So it's just too expensive. It doesn't really scale. Besides, there are probably not enough experts out there, even if you could afford paying them. So the main question, and that probably is up to 70, 80% really of these overall efforts there is how do you get the training data? How do you get the data that essentially drives the machine learning algorithm? Essentially, there are two kind of proven ways. On the one hand, the crowdsourcing, on the other hand, implicit feedback. So crowdsourcing, again, a very good academic paper on that matter. In that paper, they compared essentially quantity versus quality. They did run some tests or some annotations using Amazon Mechanical Turk. So essentially, as their tagline says, artificial intelligence, so employing people over the internet and infrastructure around that to annotate that and just having lots of them, versus having domain experts there doing the same job, and compared that with quite interesting outcome there in favor of the quantity. Of course, you can also use kind of obvious features. In this case, it would be around Hadoop, and I hope Alan is not in the room. I'm using his tweet here, just a sentiment. But being able to leverage the implicit feedbacks, what people actually do rather than what they tell us, that really turns out to be the major interesting source for that. So if you think about what the Google search engine result page does there, it actually adjusts the rankings based on the user engagement, so what you do there. And most of these recommendation algorithms are really mainly based on that user activity. So, what kind of products someone bought, or music listened to, or what ads they clicked on. And again, if you want to read deeper into that, this paper there, covers that topic in greater detail. However, we have a bit of a problem. Let's be honest, who of us has ever clicked on the second or third page of a Google result set? Oh, wow. Okay, most people don't, including myself. So the problem is that whatever is on the second, third, or whatever page, these items are typically not visible, and you can't really learn a lot of stuff from interaction, from users interacting with these items, purely because people don't really look at them. So what we would need to do in order to maximize this interaction with, or observing the user interaction, would be a way to find, to somehow push results that are hidden away in the second or third page, or whatever that means in the context of the application, to a more prominent place. And one very proven algorithm there is called Dithering. So essentially, you're initially making the overall performance worse in terms of pushing results that are in natural, normal ranking would be further down the line to a higher precision. However, through exposing these items to a higher place in the ranking, you give the user an opportunity to interact with these items, to make a vote about that, essentially. And how is that done? Essentially, you apply a log of the original rank plus some random noise, and with that you make sure that the initial top ranked are still on the top, but a few of the items who would typically appear in second or third would still be pushed within the first page, and have some exposure to the user who can interact with them. Enough with the dry theory. Let's have a concrete look at how you can implement that using two, I would say, rather standard Hadoop ecosystem components, Apache Mahout and Solr. So again, what is recommendation? Essentially, the understanding the behavior of the crowd, and deriving from that an insight what an individual will eventually do. So it's one thing to learn the relationship between items, think, as I said, books or cameras or whatever. They're rather static, right? So things like people who bought that one camera would likely also buy a battery for that camera later on. However, if you look at one specific prototypical user, Bob here, what you really want to do is to determine in real time what this user, what you can recommend this user to purchase or to listen to. And taking into account that Bob might be a user with no history at all to start with, or might be shopping for a camera right now, but was buying some baby bottle or whatever an hour ago. The question is, how can we realize that, again, using standard components at scale and in a hopefully reliable way. And in a nutshell, the setup is as follows. Mahout is used for the number crunching. I'm coming to that in greater detail in a minute. And Solr, we've implemented it with Solr, but essentially using a search engine, Solr Elasticsearch, is used for the real-time recommendations then. And that's how it looks like in practice. That's deployed, and we also have examples around that for the music domain. You essentially have the complete history, all the log files and so on in the cluster, and you calculate the co-occurrence metrics using Mahout and indexing it via Solr, so you have the index charts and item metadata available. And then you have a web tier and whatever online behavior via the recent history for a single user comes in. Solr is then used to essentially find matching items and serve it out via the web tier, coming up with a recommendation. So how does that look like? Coming back to a concrete example, let's say we have Alice, and Alice got an apple and a puppy, and Charles has got a bicycle. Now Bob comes along and got an apple as well. So what else would Bob want to buy or see? So if we step back a bit, obviously we get the interactions, the previous interactions between users on the one hand and items on the other hand through the log files, the Apache web server log files or Nginx or whatever you're using there, essentially saying this user has seen or purchased whatever this item. That we can turn into a history matrix that essentially lists all the items a certain user has seen. And there we're already entering this space where Mahout turns out to be very useful. If you compare that users versus items, to the next step, the co-occurrence matrix is essentially items by items. So essentially asking which items appear with which other items normally. And the thing is that very popular items are probably not very good candidates for doing a recommendation. So we need one more step there, and that's in our case done via the Mahout row similarity job, which essentially implements a log likelihood ratio test, and that leads us to the indicator matrix. So essentially focusing on the items that are really relevant or anomalous co-occurrences. So that's the result, that's the offline part that's pre-computed and made available, and that co-occurrence matrix is done via Mahout. And essentially, if you look at the certain document that Solr indexes, this one row from the indicator matrix becomes part of the indicator field, so you can directly update that Solr document that you have, where you have all the other metadata about the puppy, description, keywords, and so on, and adding this one indicator that is gleaned from or comes from the co-occurrence matrix. And as I said, we have implemented the whole thing as an exercise for the music domain, essentially recommending people songs and artists and albums. So we've done that with our partner LucidWorks, And essentially, you can ask things like, what would you recommend a certain user that has listened to Fats Domino and Beatles, and then through the already populated search index, it would come up with these two indicators, and one of them is apparently Jack Berry. Okay, check. Room for improvement. So as a kind of toolbox, what I can recommend there as alternatives if you want. Mahout, typically for recommendations, clustering math, as we've seen in the previous example. Webit, it's a bit harder to use, in my understanding, for classification. And Skytree is offering a commercial, so it's not an open source implementation, but it's very fast and it's industrial strength, pretty much the same line that we position our platform ourselves. So we are working together with Skytree there in that realm as well. Some operational considerations as well. One thing you might want to do is snapshotting your raw data before the training. Yields a reproducible process, and that's one of the features that we offer. Snapshots redirect on write, so being very fast and efficient and independent of the data size, essentially creating these snapshots. You might also want to consider leveraging NFS for the real-time data ingestion part. So essentially train the data on the model on the today's data, and also decoupling the learning schedule from the ingestion schedule, potentially with the snapshots. And not to forget, if recommendations are a critical part of your business, you might want to consider things like high availability of your entire cluster, data protection, disaster recovery, being able to fail over from one cluster to the other. And as I said, typically once you leave the cozy development environment, becomes actually a must-have and not only a nice-to-have on that. And one last thing I wanted to point out, if you are interested in the topics from this talk, there is a very nice free book around practical machine learning written by my two colleagues, Ted Dunning and Alan Friedman. It might be that Ted is around here, or he's at the conference, so you might get a chance to talk with him at our booth. And you can also grab these booklets over there or download it from that URL. And that was already it. I'm pretty fast today. So we come to the Q&A session. If you have a question, please use the microphone, then we can hear you all. Any questions or recommendations? There you go.
Hi.
Hi.
What kind of performance can you get with this recommendation solution?
Performance in terms of?
Speed, like for what amount of data, how much time it takes to?
I have seen ingestion rates of hundreds of thousands of items per second, so that's certainly possible. The question is also, it depends a bit on how fast can you actually deliver the log files from your sources. So I've seen more often that this is some kind of bottleneck there. But it pretty much is in that range and pretty much depends only on how fast you can ingest the data there. Any other question? Okay, so as I said, have a look at our booth, and you should be able to talk with Ted there if you have further questions around that Mahout Solar recommendation system. And I think there's the code as well available. Okay, thank you very much.